Hello, this is Lifan.
And Kieran prior.
We are doing physical pendulum today. How can we find the rotational inertia? First, we need to let an object swing on one of its axis. Many useful properties can be found, including the period and rotational inertia. And after mirroring the period of a simple oscillator, we can fit models to find interesting behaviors.
By measuring how long an object takes to complete one swing, and by knowing how that object swings about its center of mass. In a simple case, a uniform bar swinging a distance from its center of mass, as shown in the figure below, and by also using knowledge of the basic inertial properties of a rod, given in the equation, where m is the mass of the rod and L is the length of the rod.
So this is the formula of parallel axis theorem. The x here is the distance to the center of mass from the center of the point of interest, and m is the mass of the object. ICM is the torque of the rotational inertia of the center mass.
By then employing that parallel axis theorem for a rod and knowledge about how the period of small angle oscillators, we can find the period of the bar to be given by this, where x is the distance between the pivot point and the center of mass, m is the mass of the object, L is the length, and T is the period.
The x-axis in this graph is the distance from pivot point to the center of mass, and y-axis is a period. Blue point is the experiment data we got, and orange curve is a theoretical curve. The minimum point we found here is 8.1 centimeter from the center of mass, and the reason why we only got 4 experiment data is that because there are only 6 points we can access attach the bar to measure the period.
We can further apply this basic idea to find the rotational inertia of more complex shapes, such as rings of varying thicknesses, a disc, and a disc with an offset hole cut out of it. By measuring the period of oscillation and certain aspects of the shape's geometry, we can find its inertia.
The formula here is to determine the rotational inertia, and in this formula, T is the period we determined from the experiment, and m is the mass we got, g is the gravity of the Earth, and d is the distance from pivot point to center of mass.
So in this graph, our orange points represent theoretical points. The blue points are the actual points. As you can see, there are some quite big differences. This may have been due to poor measuring of the masses or measuring of the periods. It's quite hard to tell. To find the rotational inertia for more complicated shapes, we need to consider their masses. By considering that it will be one shape minus another shape, we can apply this to find its rotational inertia. For our shape, it is simply one circle minus a smaller one. By then considering how their masses are distributed, we can use the parallel axis theorem to arrive at this equation, where m is the total mass of the object, and r is the distance from the center of mass to the pivot point, and d is the distance from the center of mass to the center of the object. This makes sense due to the fact that for a disk it is slightly less than 1.5. This is 45 on 32, which is less than that, and minus 3/4 is due to the little sphere circle being cut out.
So how can we find the rotational inertia? By again applying the same theory to every more complicated shapes, we consider one with no regularity by which to calculate its rotational inertia. By considering that an applied torque can be found by formula 1.7. In this formula, tau is the torque we need, and the I is the rotational inertia, and alpha is the angular acceleration. We can use the force of gravity to apply a torque onto our ship. Since a torque is a force applied across an arm, we can rearrange Formula 1.7 for I and rewrite the net torque as Formula 1.8. In the Formula 1.8, m is the mass of the object and g is the acceleration due to gravity. A is the acceleration of the object and r is the radius of wheels used to spin up the ship, allowing us to see that the inertia of an irregular object to be given by Formula 1.9. I is the rotational inertia and alpha is the angular acceleration. To find the rotational inertia of such a complex ship, we need to find values for all of the variables in Formula 1.9, and we can get that from Pascal Capstone software, which allowed us to obtain a value of 146.79 microkilogram meters squared.
That's it, everybody. Thank you so much for listening. We hope you learned something.